Okay, thank you very much, and thanks for the organizers for this nice invitation. And so this is a joint work with Stas Miro from Geneva, and I have to say that unfortunately this is still a little bit on progress, so I'm working hard on this. So, but it's actually good for this workshop and program and for the institute. So now I can thank you in the acknowledgements. So what I'm going to describe today is how to understand the full picture here. So how to describe the law of the entire thing in the scaling limit, and how to show that this picture is conformal invariant. But so I took just a modest goal to explain sort of most of the picture or positive fraction of the picture. So I was going to explain all those pieces of this picture which just touch the boundary, so that there are slight technical differences in two cases. Okay, so let's start by FK model, and this has been already here several times in Wendelin's talks and Wendelin's talk and in Hugo's talk this morning. So so basically you start by these lattices. So we have the black octagons or squares. So here there is just drawing that we start from the checkerboard coloring. There are black and white squares, and then we just a little bit increase the or somehow resolve what is happening in the corner. So basically black squares, they form a square lattice. Their dual lattice is the lattice of the white squares, and then the medial lattice is formed by these edges here in the checkerboard coloring, and so that's the medial lattice, and then we modify by introducing these small squares. So now we look at these random cluster configurations on these edges connecting the black squares or octagons. So the configuration is omega, so it's either the edge is open or closed, and we give this kind of weight per each open edge, and then we count the number of clusters and weight by Q2 number of clusters. So, and there are as is in Hugo's talk, there are some boundary conditions. So here I selected wired boundary conditions, but actually this is you can also look at all free boundary conditions, as I will say in a moment. Okay, so you look at the configurations where you have these edges already open, and so here is a sample of configuration from this measure. So P is a so Q you should think it will be a fixed parameter, and P you can vary, but we will select it to be the critical value, which was also mentioned this morning, and we concentrate on the case Q equals to 2. Now we define the loops, the loop representation of the model. So these are basically the on this modified medial lattice, they are simple paths which go around all these clusters, so both inside and outside of these clusters, and so you can write this probability in terms of just loops and open edges in this way, and this critical value is the value when that thing vanishes. So for the critical value you get only the square root of Q to number of loops. And here I show that this is the dual configuration. So this was the original configuration, and this is the dual one. So these are really interfaces between the. So these red loops are interfaces between the open clusters and the dual open clusters, like that. And this is the also the self-dual value. So actually, the other point here is to say that we can also look at all free boundary conditions. Since this configuration is FK with this probability, but now with free boundary conditions. Okay, and then I quickly mentioned that that usually when you study all these models and you want to study the random geometry of the interfaces, you start from this kind of caudal setup where you have you piecewise fix the boundary conditions, like in Ising model you have plus spins and minus spins on these boundary arcs, or here we had the free or wired boundary conditions. So in our case it will be wired and free there. And then we fix the shape of the domain, and we fix 2 points where the boundary conditions change, and then we take the scaling limit. So this is the notion of the scaling limit. And here I just quickly illustrated the role of the parameter. So in this sense of these interfaces, when you tune the p equals to pc, you get something which has a non-trivial scaling limit, whereas so this is related to this first picture drawn by Wendelin yesterday. So if you take subcritical or supercritical p, then you will converge to this all white or all black picture. So for the interface it means that it sticks to the boundary, either the left side or the right side. And here is so this was the same list was in Clément's talk yesterday. So here are some conformal invariance results. So basically by results of Smirnov and Chelkak and Smirnov and Chelkak and co-authors, including myself and a couple of other speakers that you have seen. So the spin Ising model and FK Ising model in this caudal setup, they will converge to SLE3 and SLE1603. And here I just mentioned how to prove this. So for the uniqueness, so basically how to characterize this scaling limit, you use these discrete holomorphic observables. So and their conformal invariance. And for this existence, you use some kind of tightness arguments. So you need to have some kind of estimates of for some kind of crossing events of interfaces. And there are some generalizations for more general boundary conditions. So you have boundary conditions not changing at just 2 points, but maybe 3 points or more. But then there are of course other types of results on conformal invariance. So already it was mentioned this correlation functions result by Chelkak and others. And then you can also consider sort of collections of this interface. So try to describe an infinite collection of interfaces, so in the scaling limit. And here this is the topic of this talk, and also it was mentioned yesterday, the work of Benoit and others on spin Ising model with free boundary conditions. So what I want to do here, so this is the FK configuration, and then I just take the loops which I had, and then I try to describe this set of loops. So basically, in some sense, these are the first generation, and then I still restrict those which touch the boundary for some reason. So actually, this is just sort of, we want to have a first first step, this one, and even the second step might be even easier than this one. So this in a rectangle, and here I just have drawn those which touch the bottom of the rectangle, but there are of course many others. So basically we want to start from some domain and fix some point in the domain, and suppose that these discrete domains, so consisting of those octagons, they will converge suitably to some continuum domain. And then we consider first of all these loops of this FK Ising, but then we restrict to the sub collection. And then I map my collection to the unit disk, and then so this is the result on conformal invariance. So I say that this collection of loops converges in a suitable sense to some random collection of loops in the unit disk, and the law of this is independent of how I chose the continuum domain or how I chose to approximate this domain. So to get to the full collection, you either have to iterate this result. So now you had the sort of those loops in the first generation which touch the boundary. You have to then in all the connected components you have to repeat this process, so you have to iterate this. So that's the one way to get the full collection. But you can also work with some other so really closely related techniques, similar observable but for the interior. And the law is given by this kind of exploration tree process. So I will come back to that in a moment. But especially so you can interpret this way that the scaling limit of the full collection of the loops is the what you would expect based on this conformal invariance assumption, that is the CLE with kappa equals 16/3. And basically here are some remarks on this result, so how to put it in perspective. So we describe the full thing sort of directly, not by sort of cutting and pasting some nice pieces together, but we can work with all the sort of infinities in this business. So there might be some really tiny loops and so on. So that doesn't matter us. So and this is sort of a canonical approach. So we use this exploration tree and these SLE type methods also directly. And then we don't use any knowledge about the caudal case. So basically this fact that this SLE kappa -6 process arises, it's just a result of a calculation. So it might be something else. And I here just mentioned what I call Schramm-Sheffield principle. So basically, if you take the caudal setup for the scaling limit, then you would get SLE kappa, so this caudal SLE. If you generalize the boundary conditions so that they change a little bit, so they change at 3 different points, then you get the SLE kappa rho. So this would be Schramm's principle for 3 boundary points. But there is a one special process of these, which is this one, which has this target independence property, and it was argued by Sheffield that these CLEs should be described by SLE kappa -6, but a branching version of that, so some kind of tree. So I assume now that you are all familiar with this. So this is just a basic definition of SLE. So you have some curves growing in the upper half plane. You encode them into these conformal maps GT, and they satisfy the Lerner equation, and the driving process, which I call UT, is a Brownian motion. So there's this variance parameter kappa, and capacity parameterization here means just that this is 2. Yeah. But then there are some variants of SLEs. So this SLE kappa rho. So we want to describe this also beyond the times that these marked points might collapse or touch each other. So we define it in this way. So you take a Bessel process of dimension d. So the solution of that stochastic differential equation, and then you define ut, which was the driving process, and vt is the other marked point. So you define them using this formula. So this is basically just the Lerner equation for v, and then you say that the difference of v and u follow the Bessel process scaled like that. And here I just know that so like in the previous slide we had driving process was the Brownian motion times the variance parameter. Here the diffusion part of this driving process is this square root of kappa times dBt. And this one I just here write the dimension a little bit different. So here was the formula for the dimension of the Bessel process when rho is equal to kappa minus 6. It's that kind of formula, and in this range when kappa is between 4 and 8, the dimension is between 1 and 2, and for instance it means that this integral is well defined. Okay, and then I here just mentioned that there are more general drifts, so you can take quite arbitrary function z, which is called the partition function of this particle SLE, and if you what it means is that you take this kind of diffusion part plus this type of a drift path. Okay, so what is the exploration tree? So now this is for the FK model. So there is a sort of similar construction in the continuum. So using these SLE processes. So the definition is due to Scott, and so basically we have a collection of curves, and we have some root point. So we want to describe these loops. So we have some root points. So here fixed. So I sort of make a small cut and open my domain near the root point. Then I have the target. I also open the domain in the target, and then I start to follow these loops. So this is how I follow the first loop. Here I would turn away from the target point. So this is an event of branching. So now I instead of following this one, I start to follow the loop which was next to that. So basically here I know that this loop can't anymore go here, so I jump to the next loop which is there, and I follow that loop somewhere here. Again I need to jump, and eventually I get here. Then I take some other point and do the same thing. And what happens in the end? So I have there's a root point, and then from the root point to all the other boundary points, there are these branches of my tree. and this is a tree, so it branches at these boundary points, and we follow the same path. So if we take these two target points, W and W prime, we follow the same path until the first time that there is this process will disconnect these points. Then one of them turns, say, here, and the other one goes there, as we saw. Okay, so I here show the sort of the setup for our observable. So we work with this kind of domain. So the motivation clearly comes from this. So this is the domain which we want to consider, but we can consider a family of these. So it's a bit more general. So we take A and B further away possibly, and C and D possibly further away. So always when you start to grow this process from A, then these points will separate, so you will come to picture like this. And now we also want to so here in these points the boundary conditions change. So here are a wired boundary, and here there is free boundary. But then it actually makes sense to introduce this kind of connection between A and B, and this actually relates to this morning. Hugo, in his talk, he said that the boundary conditions, they are partitions of the boundary. So here we partition the boundary so that these points and these points, they actually belong already to the same cluster. So when we are counting the number of clusters, we count these to be of one cluster. So that's another explanation of this. But we'll see in a moment how this goes. Okay, so still a little bit more about tree. So here are the boundary touching loops, and this is the process from the bottom left to bottom right. So we follow the loops, and then we jump to the next loop. So this doesn't trace all the loops, but actually it traces many of them. But now if we want to see something here, then we take a new target point here, and then it will continue here and hit somewhere here close by. So we will actually recover all the loops. So there is an inverse map of this process. Okay, so now I will define the tool that we need. So basically, the picture looks like that. So we have some interfaces starting from the boundary. I call gamma 1 the one which starts from A, and gamma 2 the one which starts from C. And then there is this external connection between B and A. So if we go in from B, we come out from A. And then this branch, as I defined it, so it will follow this gamma 1, except that when it turns away from the point D, then we have this branching and we jump to the next loop. So there's some new gamma 1. And depending on what is sort of the internal arc configuration, so whether we connect by these interfaces C to B and A to D, or that A is connected to B and C is connected to D, we define this gamma hat this way. So basically, gamma hat will be the interface starting from C and ending to D. But if we happen to connect C to B, then we also count that the external arc connection alpha is part of gamma hat and also gamma 1. So it always includes gamma 2, but if gamma 2 goes to B, then it also includes alpha and gamma 1. And then we introduce the sort of the standard observable introduced by Stas, but now in this setting. So we look at this winding of this gamma hat, and we take this fermionic observable that there is this indicator that the edge E belongs to gamma. So E is a edge in this medial lattice. So and then we have this E to I 1/2. So this was the sigma of this morning times the winding. And this is independent of the choice of alpha. So if we had made another choice of alpha, so alpha is connecting B to A, but we can go around externally, but that changes the winding by 4 pi, so that it doesn't matter. But this is just a side remark, so this is not important. Okay, and then we define also sort of conditional versions. So we maybe I should. So we start to follow our branch gamma, and at time t it's somewhere there, and this omega t is just the domain which remains to be explored. And so first process which I consider is this nt, which is just the value of this observable at some edge. And we need also another process mt or mt plus, which is the crossing probability that which in this picture meant that we are in this case. Okay, and this is sort of visible in this F, but I want to highlight that this is the other process which I consider. Okay, so they have a martingale property, so the conditional expected values are martingales naturally, and these type of quantities which I defined, they are conditional expected values of because of this domain marker property of our model. So what we so when we explore, we basically just get the knowledge that there are some open edges on our left and some dual open edges on our right. But that this remains we can formulate it in the same form of probability measure. So these are now martingales at least up to this branching times, and we could also view them as martingales if we grow from C or from D. But we want them to be martingales for all times for this branch. So we need to see what happens on this branching event. So we need to say what happens here. And the reason is that we are now basically doing some surgery for our probability measure, so it's not clear that these quantities remain martingales for these steps. So let's see what happens there. So we have these two pictures. So this just means that C and D are somewhere here on that side of the picture. We have arrived to some boundary point V, and then we either have to turn to E2 or E1, and you can think about that all the configurations are the same outside of these boxes, so only difference is here. So basically, if this E1 is part of this gamma hat, so part of this path that was weighted by our observable, then we can count that. So this is a interface, and this is a loop. So here there is sort of one loop, and in this picture, the whole thing here is a part of this interface. So I call this a loop since we had this external connection alpha, so we were counting this piece which was touching A and B as a loop. So here we decrease the number of loops by one by doing this surgery. But the same is true for the other option that E was part of one of these loops and not gamma hat. So also in that case the number of loops decreases by one. So here there are two loops, and here there is only one. And also the winding remains the same. And actually here we can calculate even the probabilities of seeing these pictures. So they are given by this formula. Okay, so now we arrive to the boundary point, and we see what happens to the value of this MT plus, which was this crossing probability. This is just the expected value, and we see that if we turn right, then we can no longer have this connection, so that this is 0, and the probability of the left turn was this, and the value after that is something. So we need to somehow balance this factor to have this martingale property. So we balance it by introducing some coin flips. So these are plus minus 1 random variables. So if we take the absolute value of MT, we will recover MT plus. And these are IID coin flips with plus 1 with this probability. And then the definition of this MT is that we have these random coin flips sort of per excursion, and then there is this MT. And this has the property that the expected value is such that it balances with this, and we get the martingale property. And there is another interpretation of this probability. So if we just go along, not along the branch, but along the gamma 1, we see whether it turns left or right, and we flip a fair coin. So this is another way to see. So you can check that the fair coin, if you just look at the gamma 1 and not this gamma, so this branch, then you can see that it's a fair coin. And for this other observable, so this basically this fermionic observable, it was looking at whether we go through some edge here. So actually this remains constant in this branching, so basically it doesn't care whether the length of this interval AB is 0 or 1, or so this opening this next loop doesn't change the value of this interface, the value of this observer. Okay, and now we want to take the scaling limit of this, and we want to show the conformal invariance. So this follows just the this Smirnov's work. So the value of this observable is on certain edge is restricted to some line in the complex plane. So this is the first observation. The second observation is that if we sum the values of the observable at 4 neighboring edges, so B is here the center point here of the small square, and it has 4 edges coming from it, then this sum is these sums are equal. So this is the what is called strong holomorphicity, since it implies the holomorphicity for this function defined on the vertices by requiring this. So this allows us to show the conformal invariance of the scaling limit of these observables. So basically, you take the square of the of this observable, and so absolute value squared, and use that to define these almost discrete harmonic functions h. So you fix the value of h somewhere, say here 1, and then you extend it by this to rest of the domain. So when you go from black to white, you decrease the function by this value, and when you go from white to black, you increase by this value. And so this defines this function h, and you can see that or you can interpret that it's a discrete integral of this f squared. So that's the interpretation of this function. And then you can take limits, and for this f function, so this actual observable, so you could take the limit of this integrals of f squared, but then you can take the scale limit also of the actual function f, and it will be the its scale limit will be phi prime, where phi is any holomorphic function which has as an imaginary part of this function h. Okay, so these scale limits of these h functions, so they have piecewise constant boundary conditions. So here it's 0, so you always go through this h. So here it jumps by 1. Same is true here, it jumps by 1, and here it jumps by some constant which is between 0 and 1, and it's actually related to this. So this was f squared. So this is the connection or crossing probability squared. And so the only free parameter here is beta, but that's actually also determined uniquely by our setup. And one way to see this is so one way to see this is that so if you come with a certain winding, so close to B, you come with certain winding. So say you have this this phase factor, say eta, there. So that's the typical phase factor which you have. You have the external connection alpha. So here, close by here, you come typically by factor of phase factor of minus eta, and this actually determines uniquely this beta. So it means that the sign of this f divided by eta has to change somewhere in the interval, and that determines it uniquely. Okay, and I distinguish two cases. So there is this 4-point case where A, B, C, D are at macroscopic distances, and 3-point case where we collapse these points C and D, but then we need to renormalize. So basically, first of all, we take 1 minus this h. So here there is value 1, and here there is value beta. But if we shrink C and D to 0, beta would go to 0, and we would have just h equal to 0 as a limit. So we need to renormalize by some factor, and one way to see this is that you use the martingale property of this thing when you grow these arms from C and D. So you suppose that on this event A there are some macroscopic arms starting from C and D, and then you see that this value is an expected value like that, or proportional to expected value of that, and these are now you have to renormalize these by this to get something non-trivial. So you need to renormalize by the probability, but you actually want to renormalize sort of independently of your domain A, B, and T. So you need to take some little bit larger domain which agrees with your original domain in the neighborhood of C and D, and use the value of some observable in the larger domain. Okay, so you get some scaling limits, so you can write explicit the formula. So I changed a little bit here the normalization. So there is no 1 over pi in the front and so on. And if h is so here are some formulas for the upper half plane for this observable. And if h is imaginary part of some phi, then f is phi prime, and then you have some kind of from this formula you get some kind of conformal covariance for these f's. So you get these conformal factors, and from this normalization or renormalization at C you get also some conformal factor at C whenever it makes sense. So maybe I don't want to enter the discussion here. So now we want to take the scaling limit. So it's a two-step process. So we first I describe you sort of this existence part. So we consider the space of curves. So that's where our random branch of our tree is living, and this is the topology there, and we want to show the pre-compactness of this sequence of probability laws, and we need some kind of regularity, and we need to control the crossings of this annulus, and there is this kind of idea that you can sort of, so here's your domain, and you are looking at some annulus or component of annulus, and you are looking at whether your interface crosses this annulus or not. And then there are several cases. So in this case you will certainly cross, since you are going, if you are going from A to B, then you are certainly going to cross. So this is in the caudal setup. And if the thing looks like this, so the probability can be either high or low to cross this. But if the picture looks like this, then there is a positive probability to fail to cross this annulus. And the property here is that this component of this annulus is not separating A and B. So there are some connections from A to B without even touching this annulus. So this is the idea of this condition. Here is just a conditional version of this. So here, if we have observed this gamma, we ask what is the probability that it will cross these red parts here, and we ask them to be bounded away from 1 by some constant here, 1/2. And this is equivalent to the fact that there is this kind of power bound. So there is some delta, some positive delta. This goes to 0 as R2 delta. And based on this, you can so we were following Eisenman Burchard's results. So we can show that we have tightness in this space, so we can parameterize our curves Hölder continuously. And also that if you consider them as Lerner chains, the driving processes are sort of regular enough. So actually, here we note that it's as regular as Brownian motion. So any exponent less than 1/2 will do. And then there is some other little bit some other results. So it says that certain event has small probability, and the event is this kind of we call it 6 arms event. So now here there are 3 first crossings are totally fine, but the 4th and 5th one are not fine, since if this opening is infinitely small, this part is not visible from the target point, and we can't use the Lerner description for the entire thing. And here I just say that for this case, so for this 4-point or 3-point case, we need different kinds of estimates depending on where this annulus is. So we need this type of crossing estimate for our FK model. So that so say this is wired boundary, and these are open. This is a open connection here. This is a dual open boundary or free boundary, and there is a dual open connection, or that there is sort of a mixed boundary, that there are both a free and wired boundary, and say dual open or open connection. And so we need some results by these people. So especially here in this case, we need the result by Chelkak and others. Okay, so how do we use all this? So now we have basically everything. So we have basically some kind of tightness. So we know that there are some scaling limits, and we know that these scaling limits are nice. So, but we don't know the uniqueness. So next thing is the uniqueness. So we take the observable. Now I have moved C to infinity. And I consider now I'm now growing in this upper half plane my branch. So there is the point which corresponds to the tip of the branch, and then there is the point which corresponds to this other point. So when we made the small cut, so there was this other point which remains still. So, but now if we map by this Lerner map, it goes to somewhere, some dt, and this is the formula for our observable at time t. Okay, and here I just say that this vt satisfies the Lerner equation. at least when t satisfies these conditions, so that the points are not touching at that time. And this unique value of beta is in this case 1/4 of b minus ut. And so this was also related to this crossing property. So m squared was square root of beta, but I just defined it now a little bit differently. But this is essentially the same thing. And then we take the leading coefficient. So this comes from the crossing probability interpretation, and that was a martingale. And this has to be a martingale since we take the leading coefficient of the expansion, and it will be this one. So these are martingales, and now we have to remember that there were these ±1 coin flips, and here actually they are now unbiased coins, since we have if you take a product of infinitely many biased coins, then you will get unbiased one. So there are sort of infinitely many branchings happening. So actually here these are independent for each excursion and unbiased. So now we have a sort of martingale problems that. So first of all, we note that the MT is 0 whenever ut is equal to vt, and then we note that so that's the those times where we have less control of what happens to vt. But now we have to describe what is the process mt if mt and mt to 4th power minus 8t are martingales. So basically here, since this is a convex function, and its second derivative vanishes, so and this is a strictly increasing process, so that actually implies that this is pushing always instantly this process mt away from 0. So you have this kind of property that the expected value of the time spent at origin is 0. And we can use, so this is a martingale. So actually we have even nice estimates that for these processes. So it's a continuous martingale, and we can use it to define a Brownian motion in this way. So there is some sigma t process, and it actually has to be this process, otherwise nt wouldn't be a martingale. So now we know that if we define xt in this way, so basically something like mt squared, and then do a little bit Ito calculus, we see that this satisfies this stochastic differential equation. So this is a Bessel process of dimension 3/2, and in other words, it's a Eseli-Kappa-Rho process with so the growing branch is a Eseli-Kappa-Rho process with these values of kappa and rho, and then you just calculate that rho equals to kappa minus 6. Okay, so that was the process which described the difference. So actually here I just cut a little bit corners, so this was just the calculation of going from d to rho, but there is actually one more point. So we have shown something like this, but actually what I said about Vt is that it satisfies the Lerner equation whenever these points are not the same, but when they are same, I don't have basically any control on that. So it will be an increasing process, but that's it. So there might be some AT, and this AT is constant on each component of my time parameter when so each component when xt is not equal to 0, this remains constant, this process. So this could be some kind of Davis staircase type of function. So there is a contour set, and this AT is some increasing function. So it increases only in the contour set. So is this a problem? So the answer is that it's not a problem. So suppose that the AT is a Hölder continuous with some exponent p, and this AT is not identically 0. Then we know since xt was a Bessel process, we know the dimension of this set of times, and we know that then p, if it's a Hölder continuous function, p has to satisfy that it's less than minus nu, which is some variable in describing the Bessel process, namely d over 2 minus 1. So and this number is 1/4. And what I said earlier is that our ut is Hölder continuous for any exponent up to 1/2. So actually this can't be there, so it has to be identically 0. Okay. And similarly, we can work with the 4-point case. So here is the observable, here is the observable at time t. So basically c is now w, and wt is now w at time t. This is the unique value of beta. Then there are these simple martingales. So this is the crossing probability, and this is the leading coefficient of this martingale, this observable. And these are martingales, and these are some monotonic processes, yt and wt, and then you have this kind of formula for this martingale. And now you ask the same question. So when are these? When it's possible that this is a martingale and these are martingales, and now yt are something which I say here. So yt are given by the Lerner equation, and then we know that they are continuous and strictly increasing. So w is strictly increasing for all t, and yt whenever this empty is not equal to 0. And also here, in the same way, it spends 0 time at the origin, this process, this mt. So this is a convex function which has vanishing second derivative, and this is strictly increasing. So you can show this, and this is the value of this diffusion constant here. So if you plug this into the expression of this xt, then you get this kind of drift, quite complicated looking drift. And so just to check that we get the same answer this way, so we take the limit that the xt or yt goes to 0. So xt was the, maybe I didn't emphasize this enough. So xt is now in the same way the difference between b and a, and yt is the difference between c and b, and beta was given in terms of xt and yt. So now we take the limit that this ratio goes to 0. This is the limit that c goes to infinity. So then this from the formula of mt, we see that this is roughly equal to that one. And if we put this back to here, so this is something small, we see that the equation for xt becomes the same equation now for this Bessel process, a little bit different normalization. Okay, so So some remarks. So first of all, this complicated looking rift. So you can write it, for example, in this way. So you take this kind of function. So just define this like this, where yt is now difference between w and v. So or c and v. X is also in the same way. So difference between b and a. And m is what was the formula before, but you can write this type of formula for z. And now if you take the derivative of this, or you take the logarithm of this and derivative with respect to u, you get the drift of this SLE kappa z process, and you get this type of drift. So you can interpret it as a SLE kappa z process. Okay, and the crossing probability was also here involved. So if you are interested in the crossing probability, it's also here. So it's square root of m, square root of v. Yes, which is m. Okay, so the next remark is about sort of what we have done. So for this sort of little bit generalization of the chordal setup, we managed to describe our interface, and we managed to describe our interface also beyond these times that these mark points touch each other. So this is the what we so far succeeded. So next we of course want to apply. So this was the result about one branch. So we want to say something about the whole tree. So you can similar a priori estimates give you the tightness of this tree in suitable topology. So this result gives you the convergence of all the finite subtrees, and you also have some kind of control how well these finite subtrees approximate the full tree. And sort of combination of these two facts then give you the convergence of the. So you have the some scaling limit of the of your tree, and then you have some scaling limit of your finite trees, and then you know that these limits are close to each other. So this gives the convergence of the expression tree. And then there is this you need to give some estimates also that you can recover the loops in suitable sense to get the boundary touching thing. And then I want to say that you can use this either this result or the interior observable to get this radial expression tree. So going from boundary point to interior point. And actually this observable is in some sense even nicer, so you are sort of more free to play around with this interior point, since it's a smooth domain here inside. So there are some, of course, problems with the boundary observables which don't exist here in the case of the interior observable. Okay, I think I'm done. Thank you very much.
Is there any link with CLE? Can you say something about this?
Yes. So this expression tree of this branching SLE expression tree, and how you construct the loops out of this continuum expression tree that gives you CLE for kappa values. So that gives you this. So that's sort of the best way to construct these CLEs for kappa larger than 4. And this was basically the same construction, but in discrete, and we we showed that discrete expression tree converges to continuous one. So this is basically the result that the limit is CLE. So these are the boundary touching loops of the CLE 1603.
So once you have this result, why can't you just say that you can iterate and explore all loops?
Yeah. So let's see. I don't know if I have a good answer, but you also in that case you have to sort of worry that you exhaust the whole CLE. So you find all the loops, so that it doesn't happen that you sort of there are some places where you make an infinite amount of iterations, but you don't reach the target.
Any other question? Thank you again.